These three are formed by 2s 2p mixing, and these are formed without 2s 2p mixing. Let us see the total number of electrons. Here 10, 12, 14, 16 and 18. Write down their molecular orbital electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px1 equals to pi 2py1. And in this case, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equals to pi 2py2. And here sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equals to pi 2py2, sigma 2pz2. And O2 molecule, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 equals to pi 2py2, sigma 2pz2. Sorry. Pi star 2px1 equals to pi star 2py1. And the last one is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 equals to pi 2py2, pi star 2px2 equals to pi star 2py2, because two more electrons are added here. Now let us see their bond orders. In B2 molecule, bond order is 1, that already calculated. C2 molecule 2, N2 molecule 3, O2 molecule 2 and F2 molecule is 1. So usually these bond orders stability follows the bond order and also bond enthalpy. Now let us see the bond order. So bond order is highest for the nitrogen. N2 greater than C2 and O2 both are having the same bond order. C2 is equals to O2 greater than B2 and F2 same bond order. B2 equals to F2. Next, bond length. Bond length depends on the size of the atom. So that here, size of the atom as well as the bond order. Lower the bond order, higher the bond length, and within that same bond order, so larger the size of the atom, more the bond length. Now if you take the boron and the fluorine, their bond orders are only 1. So that these two molecules should have the higher bond length than remaining all. So between boron and fluorine, larger atom is boron. That means boron bond length, B2 bond length is more than the F2 bond length. Next, carbon and oxygen, if you compare that, carbon bond length is more than the O2 bond length. So C2 bond length is more than the O2 and the least bond length is with nitrogen. Next, bond enthalpy. Bond enthalpy depends basically on the number of bond, that means bond order. So that highest bond enthalpy is associated with the nitrogen molecule. Next, bond dissociation enthalpy, what happens if bond orders are same? Now we need to calculate their anti-bonding molecular orbital electrons. So Na I am calculating. Here last orbital electrons I am calculating. Here 0 anti-bonding electrons are there. Here also 0 anti-bonding electrons are there. Here also 0 anti-bonding electrons are there. Here 2 anti-bonding electrons are there. Here 4 anti-bonding electrons are there. So we know that when the number of anti-bonding electrons increase, automatically stability gradually decrease. So between C2 and O2, though their bond orders are same, but anti-bonding electrons are not here. Anti-bonding electrons are here, which makes the O2 molecule less stable than the C2 molecule. That means we need the lesser energy to break this double bond in the O2 molecule than double bond in the C2 molecule. So that bond dissociation enthalpy of the C2 is higher than the O2. Next, when you compare the boron and F2, though they are having the same bond order of 1, but here anti-bonding electrons are 0, here anti-bonding electrons are 4 are there. That means boron is more stable than the fluorine molecule. So B2 bond enthalpy is more than the F2. So it looks different. Why? Because usually what we say, higher the bond order, higher will be the bond length, bond dissociation enthalpy. But in these particular cases, when bond order and bond length, bond order is a different order we are following. Bond length is higher for C2 than O2. Bond enthalpy also higher for C2 than O2. So when bond length increases, usually bond enthalpy has to decrease. But in these cases, bond length purely depends on the atomic size. Bond enthalpy depends not only on the bond order but also on the number of anti-bonding molecular orbital electrons. Now, let us see their magnetic behavior also. What about the B2 molecule? Unpaired electrons are there. So this is paramagnetic in nature. Here, no unpaired electrons. This is diamagnetic in nature. Here, no unpaired electrons. It is diamagnetic in nature. Here, unpaired electrons are there. So it is a paramagnetic in nature. Again, here, no unpaired electrons. It is diamagnetic in nature. Dear students, I hope you understand this video. If you really understand my video, please do like and share it. Subscribe the channel and we shall meet in the next class. Thank you one and all.